Next topic will be the future of mass timber construction. And we have as our special guest an architect, an urban designer, and a zero carbon building pioneer, Craig Appelegath. He's a founding partner of Dialogues Toronto Studio. He is internationally recognized for his design and advocacy of zero carbon regenerative buildings and cities, as well as mass timber design. Craig is also active in the design community as a founding board member of Sustainable Buildings Canada and the past president of the Ontario Association of Architects. We're glad to have Craig with us. Thank you, Craig.
Thank you. Thank you for that introduction. And thank you all for showing up early Friday morning before one of our last summer weekends. Wow, you're committed. You're committed. So I'm hoping that we can provide you with something that worth your coming out today. And by the way, Luigi, walking in and seeing that building going up, it's gorgeous. You guys should be really proud of that. That's very, very cool. Well done. So I'd like to talk today about the future of mass timber. And the future of mass timber is low carbon hybridized mass timber structures. So hands up, those of you who know what this number stands for. One hand, any other hands? What does it stand for? That's correct. This is the number of the concentration parts per million of CO2 in the atmosphere calculated by James Hansen in 2008 at the NASA Goddard Space Research Institute. That would be a sustainable amount of carbon in the atmosphere for us not to experience climate change. This is what it is today. We've got a problem. You know the details. We're right now passing the 1.5 mark centigrade increase in global temperature. This is the latest example of the impacts of climate change right now. I think Greta said it best. Our house is on fire. I am here to say our house is on fire. So all of you and our practice are asking the same question. We were asking ourselves about 20 years ago, started asking ourselves, what can we do as a practice? What can we do just as an architecture, engineering, and planning practice to have some impact on this challenge we face, this huge existential challenge? So as many of you have, we joined the 2030 challenge, the AI 2030 challenge, and are benchmarking our building energy efficiency against others. And as you know, energy is a proxy for carbon. But we also said, look, one of the things we can do as designers is design with materials that reduce the carbon emissions in their life cycle. So from the production, harvesting, all the way through to decomposition. And wood and mass timber is one of those materials, clearly. So some of the buildings, to give you a sense of who we are and what we do before I jump into hybridization. This is the UBC student sub, lovely building, a hybridized building. Here you can see concrete columns, wood and steel trusses, and CLT. This is the first building I worked on, started 12 years ago, finished 12 years ago, the Bill Fish Forest Stewardship Center. This was a bear of a building design. It's only one floor. It's only $7 million, but it was the first in Canada 7-petal living building challenge. That meant it's zero energy, it makes its own energy, and zero water. The water that we used in the building, or that they used in the building, is regenerated. And it meets the list of 25 red list of building materials that you can't use because of their contamination in the environment. That was the hardest target to meet. But they produce wonderful buildings. It's just, as soon as I walked through this building as it was being constructed and built, I thought, oh my goodness, this is what I've got to dedicate my career to. This stuff is not only gorgeous, but it just rings all the bells for what we're trying to do to reduce carbon. This is a building in Vancouver that is currently being worked on by our Vancouver studio, 2150 Keith Street. It's a commercial building, commercial office building, cool structure. And this building, this photograph was taken about a week ago. The building just opened. It's the Centennial College's A block. It's a $100 million, 6-story mass timber building. The first zero carbon post-secondary higher education facility in Canada, constructed. Look at it. It's just gorgeous. It's so nice to be in. And interesting, I was talking last night to our table. One of the things I noticed when we were walking through on our weekly meetings, all of the trades are so much more respectful of what they're doing. It's a quiet site. It's a very neat site. Everyone seems to care about what they're doing. The construction was just wonderful to watch. And this is a project that I led the team on. We just won the competition for Seneca's Health and Wellness Center. It's a health and wellness and recreation center, $100 million approximate budget, indigenously inspired. We're working with 2 Row architects as well, collaborating with them. And it gives you some sense of the versatility of mass timber. But do you notice something that's missing from all these examples? And I suspect from all of the examples that you've been seeing over the last day. Tall buildings. So as a practice, we said to ourselves, well, okay, it's okay to be designing low-rise and mid-rise buildings in mass timber, but in urban settings, tall buildings are the buildings that use materials. How do we use mass timber in tall buildings? What are we going to do in order to make the use of that material not only structurally viable, but economically viable? Because if it's not economically viable, it's not going to get done. Hybrid wood structures, hybrid mass timber. So in 2018, myself and a number of our structural partners sat down at one of our offsites and said, how are we going to do this? What can we do? What can we do to push the needle, to push the envelope, to move the needle, I should say, on this challenge? So this is the challenge we set ourselves. 100+ story hybrid wood mixed use, zero carbon high-rise prototype. And why 100 stories? Well, if we're 70 stories, I probably wouldn't be here today. No one would really care. But if it's 100 stories, people will care. And it's a super tall. Like, super talls are not made of mass timber. They're made of steel and concrete. So how do we do it out of mass timber? So here is the challenge. How can we design a mixed-use high-rise building using wood, steel, concrete, and other advanced materials that maximize the overall use of sustainably harvested wood by volume? The point is storing carbon. The point is using wood in high-rise construction in the most cost-effective, energy-efficient, low-carbon, and elegant manner that is also conducive to human well-being and the well-being of the environment. That was the challenge. And so this is what we came up with. Let me tell you the story about it. This is a visual rendering of what it would look like. This is up at Finch and Yonge. We put it on the Hydro Corridor site as a sort of obelisk to the entry to Toronto. This was the one discovery as we started to research and explore how to do this that rang bells for us, that floor systems in high-rise buildings are 70% of the building materials in a high-rise building. 70%. Interesting. So clearly, using mass timber for the floor system is something we can do at the same time as taking advantage of traditional tall building structural design. So this is the structural concept we came up with. It's a double tube structure. That means that there is the concrete core, traditional concrete core, and there is a steel exoskeleton And every number of floors, you can see those red bands there. Those are the floors where trusses tie the core to the diagrid exoskeleton, steel exoskeleton. And as a result, they make it one big cantilever. So that is what is taking the wind force. And I mean, I'm not an engineer, so how many engineers are in the audience here? Right, so you know what I'm talking about. So where's the wood? It's the floor system. And this is how we set it up. So we had floor panels that would be running from the core to the outside diagrid, all around the core. That's the structure of them. And this is what they look like. Oh, I'm sorry. This is the team that we pulled together. As soon as we had the idea, we said, okay, no one is going to believe a design firm on this. So let's pull together a team that really can make the prototype as real as possible and understand the wind loading from RWDI. Morgan Solar is there for the PV because the building is covered in PV to generate energy. And Alice Dawn and Mark Gallioni is going to be talking more about this in detail this afternoon. They were the partner that helped to develop all the logistics and how this would actually be constructed. What's the best way to take our engineering and turn it into reality and build prototypes, like physical prototypes for the floor. So this is the floor panel. This is the sort of the DNA of this building that makes it special is this simple panel. It's 10 feet by 40 feet, 7-ply CLT. Did you hear that? 40 feet? CLT doesn't span 40 feet, does it? But it's a hybrid floor panel. And we've hybridized it by routing out 2 channels in the CLT panel and putting in those routed out slots a cage and post-tension steel cables. So we provide for the tension, the building moment, the moment of that panel by adding those 2 tenons. That creates the panel that will span 40 feet. And why 40 feet? Because 40 feet is a commercial floor plate span required for selling commercial real estate without having columns, which is right now what mass timber does. This is what it looks like. So on the underside, you have the post-tension tendons there, and on the top, we have a concrete, a 7-inch concrete floor for 2 reasons. 1, it becomes part of the actual structure, and 2, it's for acoustical reasons. And this is what it looks like. So completely open space. And you get to see the CLT, which is what all the realtors were telling us and developers were telling us they wanted to see. And during the process of doing this, we went to Cadillac Fairview and they sat down with us and we said, we want you to crap all over this. We want you to be as harsh a critic as possible and tell us what you think of this process. And we did this with Alice Dawn. We met with them. And they said, well, instead of commenting on your building, why don't you just design us a building that's equivalent to a building we're doing right now? So we took a building that we're doing right now, a 40-story building, used the system, and then they cost it. And they said, well, it's, from what we can see, about 5 to 10% greater in cost. But that does not take into account any sort of carbon pricing. But they said, at that rate, we could probably market it. So keep going, guys. So here's the value proposition. Typical CLT timber grid, 20 to 30 feet, columns. Hybrid timber floor panel system, 40 feet, no columns. So we thought this was a cool idea. And then I got a phone call from Fast Company in 2021 saying, we've seen your project and it has been, was nominated and then voted as the most innovative idea in the world of 2021. I said, are you serious? Really? They said, yes. But Canadians don't tend to take themselves very seriously. We don't think that we can do innovation, world-class innovation, but clearly we can. So here's the structural testing. It's one thing to have an idea like this, but it's another to really make sure that it's viable. And that's where Ellis Dawn and FP Innovations, who joined the team, came in. So this is Ellis Dawn's St. Thomas plant, where they're doing modular CLT and modular construction. And they set a big floor area aside. And this is a picture of all the small pieces of those CLT panels that are hybrid panels that were going to be used for testing, for structural loading, for vibration, and very importantly, for fire. So this is one of the panels that was tested for fire. You can see the cable coming out of that concrete tendon there as being the heat sensors. So when they put it in the NRC kiln and burn it, they could determine whether or not the steel was at a temperature that would support the panel as required by the code. There's what it looks like just after it being pulled off the kiln, and there's what it looks like after it's been taken out and the fire's out. It worked. It met all the requirements. So that meant we want to test the whole panel. And this is Ellis Dawn's team pouring the concrete down that trough of the panel. There it is, 40 feet long, 10 feet wide with those two troughs. That's what it looks like with the concrete and post-tension tendons in there, turned over. And this is with kerf plates. Now this is interesting. We at first thought, well, we'll put screws in order to connect the concrete topping to the CLT. But then Ellis Dawn said, are you serious? There'd be like 1,000 screws. That would take a long time. And they got our engineer to take the screw and put one in. It's like, want to do 1,000 of those? So what we came across was the notion of putting in kerf plates. And these are steel plates that get slotted in. And they do the work of connecting the concrete in shear to the CLT. And this is we built two, or Ellis Dawn at their plant built two of these panels and connected them together because we wanted to test them in unison, because they're not going to be separate when they're in the building. They're going to be together. So we want to test them. Look at the scale of this. And this is out in BC. So these got shipped out to BC, and they're doing at UBC Structural Testing Labs. They have really great CLT test sites there. Too bad we don't have that in Ontario. So, 3 thoughts going forward. The first one, mass timber is not a religion. It's a building material. So I've noticed over the last few years that there's been this emergence of this notion of purity, of tall buildings being all mass timber, and this race for the tallest all mass timber building. Like, engineers out there, right? Back me up on this. Timber in vertical support for tall buildings is not efficient. It doesn't work. It's whippy. You have to have huge pieces of wood, columns, to support a tall building. It's not economically viable. It's not structurally viable. So what is viable? Hybridization. So we've got to get over this notion of purity. And anyway, every mass timber building has concrete foundations, and it's got stainless steel or galvanized steel connections, right? To hold everything together. Screws, bolts, plates, steel. It's not going to go together without steel. So think about this as what is the end goal. Second, horses for courses. Different horses for different courses. In other words, there are different building types we're going to be using mass timber for. The Little Bill Fish Forest Stewardship Center, 1 floor, perfect for all mass timber. 4, 5, 6, 7, 8, 9, 10 mid-rise mass timber, great. Although the shear you might want to take up on concrete core possibly. Again, think about the building type. If you're doing a large-scale recreational center, it's going to have to be hybridized. If you're going to do a tall building, it's going to have to be hybridized. Mass timber is a building material that can be used in different ways for different building types. That's the key. And that leads us to let the relative reduction of carbon be your measure of success. The whole point here, and Veronica drove it home well with that slide that said 1 cubic meter of wood stores 1 ton of CO2. And the embodied carbon of using mass timber at this point is between 13 and 25% less than steel and concrete. By the way, steel and concrete manufacturers, fabricators around the world are racing to reduce their embodied carbon because of mass timber. I mean, at some point, they're going to find ways. For example, have you heard of New Steel out of I think it's Chicago? New Steel takes scrap metal and recycles it into steel, structural steel sections using arc furnaces that are powered by solar and wind, zero carbon. So that's zero carbon steel, or as close to zero carbon as you can get. That's because of mass timber being a competitor and the rest of the industry very worried about it. Concrete's also trying to figure out how to reduce its carbon footprint. For example, I think, did Patrick Crabb yesterday talk about the cellulose in concrete? No? Anyway, there's cellulose fibers introduced into concrete, strengthen concrete and reduce the carbon. So what mass timber is doing is not only in and of itself reducing carbon, but it is causing the rest of the industry, concrete and steel, to find ways to reduce carbon as well. So that's it. Questions? Yes?
Could you maybe I'm not an answer to the question, but could you elaborate on the algae bioreactor?
Yeah, you know, I didn't put all of the zero carbon part in the presentation. That's another half an hour. But here's how we did the zero carbon. First of all, we said, okay, this is a tall building. It's going to have south, east, and a west facade that are going to face the sun enough to generate electricity by PV. So it's covered in photovoltaics, and they account for 25% of the energy. What about the rest of the energy? So we, about, I guess, 10 years ago now, teamed up with Pond Technologies. They're a very, very innovative company in Markham. And they came up with a cool idea. Actually, the fellow that founded it, Steve Martin, used to be head of engineering here, or no, not here, at TMU. And he said, well, you know, if you take algae and put it in a tank and put high energy, low, or I said high intensity, but low energy light through LEDs into that tank, and you bubble CO2 through the tank, the algae will grow like stink. So what we've done, and they've got a bioreactor, and actually we connected them with Markham District Energy to do a combined project to prove that the Markham District Energy emissions could be then filtered out using the Pond bioreactor. And so you take a natural gas-fired generator, and you take its emissions and you bubble it through tanks that have these high efficiency LED lights in them at a frequency that helps grow algae. It's sort of a red-purple color. And the algae grows and takes the CO2 out. Well, what do you do with the algae? Well, algae can be used for a whole bunch of things. First of all, algae could then be reburned again in a cycle, or it can be used for animal feed, or it can be used for soil remediation, or it can be used for what they're using for, because they're very valuable, it's nutraceuticals. So you've got a good product that comes out of it that reduces the carbon out of that system. So you get the zero operating, and we set up, the idea was that there'd be a generation system that would not only power this building, but would help power the neighborhood around. So that was the idea. Yes? Yes, and I should have put that slide in. We were able to reduce the carbon intensity of the whole by like 25% if you don't consider biogenic carbon. And by the way, here's something that you all should be out there thinking about and advocating for, I would urge, and that is there's a hot debate right now as to whether or not biogenic carbon should be counted. And the reason for seeing it not to be counted as a fair way of reducing your carbon footprint is because the argument goes in a building may only last 25 years, which what buildings do you know other than really bad buildings only last 25 years? But if it lasts 25 years and then it is deconstructed and the materials are then thrown in landfill, that wood will turn into CO2 by decomposition. Bacteria will break it down and produce CO2. So therefore, the CO2 will be released and you haven't stored the carbon. So yes, that could happen. However, we're in a climate emergency right now, right? So 25 years, if we don't figure this out, we're totally fucked. So let's just get real and say, let's count it and let's make it part of the way we evaluate using mass timber, because it is going to help us store that carbon that we need to store, and we need to have that rationale for using more and more mass timber from sustainably harvested forested to store that carbon over that 25 years. I think it's going to last a lot longer than that. And there's another really good presentation to be had here on actually deconstructing, disassembling a building, designing for disassembly so that you could actually take that mass timber and reuse it somewhere else in its pieces. So it becomes like a material bank. Right now, the way we use mass timber, we screw it together and then you can't take the screws out. So we're going to have to actually think more carefully about how we're going to assemble our mass timber buildings so they can be disassembled and reused. Yes?
If you were to remove the concrete, if you were to remove the concrete toppings above the CLT and replace them with a dry buildup that still got you the acoustical performance that you needed, how would that affect the structural complexities that you had incorporated below the CLT?
That's a good question. I'm not a structural engineer, so I can't give you the structural answer for that, but I can say, in talking to the structural engineers they went along, what they were trying to do is maximize the structural capacity and minimize the overall cost and material use. So it would be a question of having to increase the number of layers of CLT to then take up the structural capacity that the concrete was providing. But at the same time, what the 7 inches of concrete does for you is it not only provides you with that combined structure of the CLT and the concrete, but it provides you with a way of running various systems and utilities, like you can run conduit, you can run pipes, and so forth in the floor, and you don't have to have a raised floor. Now, many of the tenants are going to want raised floor for reasons of IT and so forth, but you can run basic services in that concrete. So it was cost benefit, because the whole point here is we had Ellis Dawn doing detailed cost analysis as we went, trying to figure out how cost effective can we be? Because if this is not cost effective, it's just a big exercise in producing really cool looking stuff. It's not going to go anywhere. And so, by the way, one of the tests we did, Ivan Poloni at Ellis Dawn, who just retired, he and I sat down for 3 days and called every developer in North America. The big ones like Hines, Cadillac Ferry was already on board, and said, here's what we're doing. We gave them a sort of quick presentation. Is this something that will be of interest to you? And everyone said, yes. As soon as you've done the testing, tell us, this is really cool. This sounds great. So now, they also said, you do know that because of the pandemic, that the commercial lease rate's gone down. Like, like you really just invented something for commercial space right now, really? But anyway, that will over time change. And so there's real interest there because they're seeing so much across North America. It's already happened in Europe, but across North America, they're seeing so much interest by potential leasers for being in a mass timber building that they see it as a way of differentiating themselves from competitors. So, worthwhile. Yes. Hi, Ryan.
Yeah, hey, Greg. Thanks for the presentation. So,
In terms of the next step for the system, if we start to get adoption at scale, I'm curious, are there any manufacturers in North America that can produce these panels with their current assembly lines, or is it a case where someone's going to have to build a new factory essentially to start rolling these things out in big quantities?
Okay, so that's a really good question. Like, the first part of the question is, what are the next steps? The second part is, how would we actually do it? The next steps is for us to finish doing the testing. Like, we have not tested those big panels, the ones that you saw the Ellis Don guy standing on and our guy standing on in BC. So they're going to have to test that over the next year and a half for creep and bending and so forth and vibration. And so if it makes all those tests, we're going to try and figure out how to burn the big panels. There's no fire testing for panels that size anywhere. Actually, there is in China, I think, but we're not going to fly it over to China or ship it to China. So we're going to have to see if we can build our own and test it. But assuming it meets all the tests, what we're going to do is we're going to look for any of our potential partners or clients that want a small building. Like, we're talking to some universities right now that would love to do this in an engineering building and then have all the sensors put in so they could measure what's going on, and it could be a sort of a real lab, like a life lab. And it doesn't have to go into a tall building right away. In fact, it's probably better if it doesn't. Like, let's test this out on a small building or a low-rise building. But that is the next step. And in terms of manufacturing, where it can be manufactured, it's really simple. Like, it's CLT panels. So Element 5 can do it. Nordic can do it. MTC, the new one coming that Patrick's launching in Nova Scotia, can do it. And then it's simply, you can either do it in their CNC process, or you can simply saw route it. And so that can be done in a plant size. So right now, there's no facility set up just to do this, but you could see a contractor coming, a CLT installer like Timmerman coming and saying, okay, we could do this. We've got the capacity to take those in and do it. And again, it's like chicken and egg, right? Like, if you've got someone that wants it, someone will come along and find a way to do it. And the first few won't be as cost effective as once you get going at it. But that's what we're anticipating. And we're also going to be designing one for 30 feet too, which will, they're for residential floor spans. Anything else? No? Great. Well, thanks very much. And thanks for coming out on Friday morning. Kudos to you for getting up and